curious, observant. Imagine bending over a workbench for 8 hours a day, staring through a magnifying glass at a gear the size of a breadcrumb. To assemble a watch, a human has to hold perfect focus while hunting for microscopic defects. Over time, the biological hardware simply gives out. The muscles controlling the eye twitch, the lens strains, and focus blurs as fatigue sets in. The brain starts skipping details just to keep going. This graphic compares the physical limits of a tired human eye to a camera lens. Due to biological fatigue, human inspectors miss about 3% of defects. A machine lens, however, processes the exact object from 47 angles simultaneously without blinking. This problem scales up directly from physical eye strain to total cognitive overload. Doctors trying to cross-reference thousands of medical records, or city planners trying to manage millions of daily commuters, frequently drown in a sea of raw information. Scaling our modern world beyond the speed of sight and memory turns human biology into a bottleneck. Solving this requires more than just trying to work harder. It requires a tireless, high-speed collaborator to bridge the gap. Computer vision provides that bridge. Think of it as giving a machine digital eyes, allowing it to process and make sense of visual information without the biological limits of exhaustion. This flowchart outlines how a machine learns to see, from acquiring raw image data to detecting objects. Focus on the feature extraction phase. It isolates variables like shape, color, and texture, turning visual traits into mathematical data points. By applying those mathematical points, a vision system in that watch factory instantly scans a gear from every possible angle. It easily locates a scratch that is 1/100th the width of a single human hair. That exact same mathematical precision applies directly to human health. When a patient goes in for an MRI, vision algorithms scan through thousands of cross-sectional images in seconds. The system bypasses the surface image entirely and hunts directly for microscopic irregularities. By spotting early-stage tumors that a tired human eye might scroll past, this digital sight translates directly into saved lives. But seeing is only half the battle. To solve cognitive overload, we rely on data science. This technology acts as a digital brain, ingesting millions of historical and real-time variables that paralyze human decision-making. Consider a major city during the monsoon season. Heavy rains cause immediate chaotic traffic gridlock across hundreds of intersecting streets. By continuously analyzing historical weather patterns alongside live sensor data from the roads, data science algorithms predict congestion before a jam even forms. The system instantly calculates and deploys alternate routes directly to drivers' navigation apps. That predictive logic scales all the way down to a single student. In education, a data model tracks an individual's unique learning pace, logging when they log in, how long they study, and exactly where they struggle with the material. If a student starts missing online classes, the system detects the behavioral pattern. It deploys personalized interventions, like schedule-adjusted reminders, to pull them back on track. Data science operates as a structural foresight engine. Whether managing the commute for millions or building better habits for one student, it turns overwhelming raw information into preemptive solutions. To connect these systems, we use natural language processing. Look closely at the sentiment analysis component. Instead of simply transcribing audio, it mathematically analyzes word choice to extract the underlying emotional state of the speaker. Imagine a rescue ship out at sea receiving a sudden flood of distress calls. The audio is chaotic, and the messages are broadcast in multiple languages that the human crew does not speak. Within seconds, an NLP system translates every single incoming audio stream. Simultaneously, it flags the voices exhibiting the highest levels of fear and urgency, directing the crew to the most critical targets first. By instantly extracting vital context alongside the vocabulary, NLP destroys the language barriers that normally slow down human response times in life or death situations. But relying on speed creates a new vulnerability. Because while a computer processes information millions of times faster than a person, it lacks any moral judgment. If left entirely unchecked, algorithms become dangerous. Take algorithmic bias, for example. Between 2014 and 2018, a major tech company tried to build an AI tool to automatically review job applications and find the best candidates. The engineers trained the system using 10 years of historical resumes. Because the tech industry had been heavily male-dominated, the algorithm blindly learned that male candidates were successful and began actively downgrading applications that contained words associated with women. This creates a toxic feedback loop. Biased historical data leads to biased machine decisions, which then become the flawed foundation for the next generation of data. Machines simply replicate the historical flaws of their creators at a massive scale. We cannot abdicate our ethical responsibility to a mathematical formula. To fix this, the industry relies on a framework called human in the loop. It serves as the ethical baseline for deploying AI safely into society. In this structure, the machine serves purely as the data gatherer and high-speed analyst. An actual human operator maintains strict oversight, holding the ultimate veto and final decision-making power. You see this ideal collaboration in modern hospitals. The vision algorithm highlights a microscopic cluster of cells on an MRI, but a human doctor reviews the scan, delivers the diagnosis to the patient, and designs the treatment plan. Automating the tedious and the complex allows us to focus where machines cannot, on empathy, creativity, and the human judgment required to build a better future.